We are more than ready for the next session of the day with the company of our matecito. And let's go. We have seen the definition of the conditional expectation. And we said that the conditional expectation in terms of the information given by a sigma algebra satisfies two important properties, which are measurability and the projection property, and we basically proved them. Now, it would be nice to review this. But since I will have to review this, basically everything up to here, so many more times, let's jump straight to the uniqueness of the conditional expectation. I should make a better version of my notes, they are quite messy. Uniqueness of the conditional expectation. Let x bar and x double bar be versions of the conditional expectation given the information f, script f, let me write it better, of x with x positive. Then we have that both x bar, x double bar are measurable with respect to f. Let me write it in this way. And the expectation of v applied to x is the same as this, which is the same as that. For any v in f plus. Which means x bar is equal to x double bar almost surely. We also have that conversely if the conditional expectation given script f of x is x bar with and x double bar is in f plus, and x bar is equal to x double bar almost surely, then the expectation of v applied to x is equal as the expectation of v applied to double x, which means x double bar is a version of the conditional expectation of f, well, given f of x. And this concludes the proof. So basically the result is given by the insensitivity of the expectation, I guess. And now let's prove the projection property. Or this is just a remark, let me turn on the light 1 second. So, well, more than 1 second, just to see better. Okay, good. Okay, we have uniqueness now. Existence, no, projection property. PP. Let V be the indicator function, apparently. And X, H measurable. Expectation of X. Which is the same as this, is the expectation of the conditional expectation given f of x. Moreover, if x is integrable, then the expectation of x, right, the conditional expectation is also integrable. And if x integrable, we can rewrite the projection property as follows. Expectation v applied to x minus x bar equals 0 for any v in f plus. Now let x be integrable, then we have that x minus x bar is also integrable. And now define x tilde to be x minus x bar. And write x as x tilde minus x bar. Plus, actually, yeah. Lol. We have that the expectation of the indicator of h applied to x tilde is 0 for any h in f. And we call x the orthogonal projection, well, it should be x tilde, x tilde orthogonal projection of x on script f. Let's continue. Well, let me put it like this. Existence of conditional expectation. Consider a measure space E, script E, and mu. Measure space. And the G, measurable and positive. And define nu of A as the integral, the integral of the indicator of A with the measure mu, which explicitly is the integral over A, weighted with the measure mu, of g of x. Mu dx. This for any A. It can be proved that nu is a measure on the probability space. But without the measure. For the proof of the existence of conditional expectation, what we do is to rely on Radon-Nikodym theorem, but we will get to that. For now, let's take a look at this proposition. For every function, positive and measurable, for such measure mu and nu, for mu and nu, we have that the integral over E f of x nu dx is the same as the integral over E of g of x, so some other function integrated with the other measure. No, we actually have g of x times f of x mu dx. Quite strange, I think. Definition. Absolute continuity or continuity. Consider E, script E, measure space, and mu and nu, two measures on it. Then nu is said to be absolutely continuous with respect to mu if for any measurable set, the value that the measure mu assigns to A implies that if this is 0, then nu of A is also 0. So in some sense, nu preserves the negligible sets. question is, could it be that mu of A equals something, nu of A equals something different for non-negligible A? Is it raining? Yes, there is a. Now we have a remark. If nu of A is the integral over A g of x mu dx, then nu is absolutely continuous with respect to mu. So nu depends on mu on some sense. Okay. Theorem Radon. And let's see if I can write it correctly. Nicodim no, mamma mia, lo scrivo sempre male. Nicodim now suppose mu finite, nu absolutely continuous, and here it's implicit that it is with respect to mu, then there exists some function g such that the integral over e f of x nu dx is the same as the integral over e of, well, this is basically what we wrote before, but without the assumption of being sigma finite. This is sigma finite. F of x, g of x, mu dx. So if we integrate f with the measure nu, we can get the same result by using another measure complemented with some function. Well, complemented in the sense that we have to add also this function. So it is a quite artificial manipulation, I think. And moreover, g unique up to equivalence. How can I write up to equivalence? Up to equivalence. Which means that the above also holds for, let's call it g hat in script e plus, such that g equal g hat mu almost surely. The function g is called radon nicodym derivative. Why derivative? I don't know. Of nu with respect to mu. Here I wrote one personal remark which would be useful to interpret this, I think, and I don't know if it is correct. So the radon nicodym derivative is the function or density which makes a measure absolutely continuous with respect to another measure. So by means of the function g, we make nu absolutely continuous with respect to mu. Let me try to write it again. So suppose, well, radon nicodym. Suppose mu is sigma finite and nu absolutely continuous. Then for g positive and measurable, we have that the integral over e g of x nu dx is this. This is f. Here it is existence, g unique up to equivalence, and yeah, g equal g hat mu almost surely. Basically this is the central thing. There are a few things better in life than studying with a matter on the side. But apart from that, let's see here. With these notions we can prove finally the uniqueness, well, the existence, well, here it says uniqueness, but in the label of the theorem I have wrote existence. Well, but the theorem is about both. Existence and uniqueness of conditional expectation. Let x be positive and measurable, f sub sigma algebra of h, then the conditional expectation denoted e sub f x exists and is unique up to equivalence. Let's take a look at the proof. So, for any random variable with a subsim algebra, we have the existence and uniqueness up to equivalence of the conditional expectation. For H in F, this is an event. For any event on the measurable space omega H, consider the restriction of P on F. Consider the restriction of the measure of the probability measure on script F, and define Q of H to be the integral over H PD omega x of omega where P is a probability measure and Q P prob measure, Q absolutely continuous with respect to P. Now, by Radon-Nikodym theorem, there exists random variable x bar F measurable such that the integral over omega of, let me try to think about it, I have no idea. Q of omega, this is a measure, and it should integrate V of omega is the same as this. Now, why is this omega not d of omega? Yeah, this is d of omega. D omega. For any V. And since it satisfies the projection property, x bar is a version of the conditional expectation. And as I said, this is the key, maybe, the restriction of the probability measure on F, because we know F. Remark. Let's set V as the indicator of H with H in F. Then we have this, the integral over omega Q of d omega, indicator of h of omega, this thing is the measure of the set H with Q. In other words, the integral of x of omega over H integrated with P okay. I think I may start to understand something about this. We have an important part, properties. Let's call it property, okay, wait. Properties of the conditional expectation. One, monotonicity. Basically, conditional expectation satisfies all the ones of the standard expectation, the common expectation, plus some other stuff. So in some sense, it generalizes expectation. If x is less than y, the conditional expectation over f of x is less than the conditional expectation of y. The conditional expectation over f of this quantity, ax plus by, is the same as a times the conditional expectation of x plus e times the conditional expectation of y. And this, of course, for any a. And, well, here we can also sum c, and since it's a constant, now we have the conditional monotone convergence theorem, which I call it like this. If we have a sequence xn such that xn positive for any n increasing to x, then the limit of the conditional expectation, okay, well, the expectation of xn increases to the conditional expectation of x. Condition alpha 2. If you have a sequence xn positive, then the expectation, the conditional expectation given f of the limit of xn is less than the limit of the expectation. conditional DCT, dominated convergence theorem, if we have a sequence xn increasing to x, which is bounded, x bounded by y. Here in the notes I have put xn bounded by y, but it should be x, I think. Y integrable, then the expectation of the limit, well, the limit of the expectation is the expectation of the limit. So the conditional expectation of xn is the same as the conditional expectation of x. But it should be in limit. We could be considering the limit. Now we have Jensen. Conditional Jensen, let's call it. If we have that f is convex, then the conditional expectation over f of x is less than f applied to the conditional expectation. And as a remark, we have that all these results hold almost surely. And now we have a theorem with special properties. Let's call it special properties of conditional expectation. Let f and g, script f, script g, sub sigma algebras of h. W x h measurable such that their expectation exists. Then if W is f measurable, this implies that x bar wait. The conditional expectation of the product Wx, since this is measurable, this is W times the conditional expectation. This is called conditional determinism. And if we have that f sub sigma algebra of G, we have to play, this is the tower property. it should be correct. No, F. Oh yeah, because F is smaller here. So basically the smaller sigma algebra wins. Why? I don't know. This is also known as tower property. Okay. Let's take a break. See you later.